Hello, good afternoon. Last time we have seen the dynamic programming and its essential characteristics. So basically, two characteristics were important in this dynamic programming technique. The first one was overlapping subproblems, means repetition of the same computation. As we can see here in the figure, like Fibonacci 5 is computed here also, and Fibonacci 5 is once again repeated here. Like Fibonacci 4 is repeated 3 times. This Fibonacci 4, this is Fibonacci 4, and this is Fibonacci 4 in the computation of Fibonacci n. So fib of n is equal to fib of n minus 1 plus n minus 2 when n is greater than 2, otherwise it is n only. So this was first characteristics. And the second characteristics was optimal substructure. So as we can note here that this is the optimal substructure. So basically, if we are claiming that the path from A to B is the shortest path in the graph, and C is some intermediate vertex on this graph, then the subproblems or substructure of this problem, like A to C and C to B, this should be the optimal substructure. Okay. The various problems were covered in this category: the matrix chain multiplication, longest common subsequence, optimal binary search tree, single source shortest path algorithm, multi-stage graph, and all pair shortest path. So basically, we covered matrix chain multiplication and longest common subsequence in the previous lecture, and today we will cover this single source shortest path. And after covering single source shortest path, we will cover some of the problems based on dynamic programming. Now see, this problem is known as a single source shortest path, as we had already seen that this problem can also be solved with the help of greedy approach, and that algorithm is known as a Dijkstra algorithm. However, when this problem is known as is solved with the help of dynamic programming approach, the algorithm name is Bellman-Ford algorithm. Here we can see one graph. Suppose it is a diagraph is given 1 to 2 and 2 to 3, and 1 to 3 there are direct edges. And if we are interested in finding the shortest path from vertex 1 to vertex 2 and vertex 1 to vertex 3, and if we apply the if we apply the Dijkstra algorithm on this particular thing, then the things will not get updated here. So finally, when you come out of the solution from greedy approach, then the path from 1 to 2 is reported as 7, and path from 1 to 3 is reported as 5. But actually, we can note here the shortest path between node 1 to node 3 should be 2 only, because as we can see here, this is 1 to 2, the cost is 7, and 2 to 3, the cost is -5. So 1 to 3, probably this should be the shortest path from node 1 to node 3, and the corresponding shortest path cost will be 2. But if you apply Dijkstra algorithm on this graph, then you might get some incorrect results. Okay, this is because some negative edge are present in the graph, and this was the main bottleneck of the Dijkstra algorithm, that it is unable to handle the negative length edges. Okay, but Bellman-Ford is the counterpart of the Dijkstra algorithm, which can be solved with the help of dynamic programming approach, and it is very much feasible, or it is very much comfortable for handling this negative length edges here. So we will see how this problem can be solved with the help of dynamic programming, and what are the essential characteristics of dynamic programming, that is optimal substructure and overlapping subproblems lies here. So basically, here we define one dist of U, and in subscript in superscript you can see L. So basically, we will define this. This is nothing but the shortest path from vertex B to vertex U by considering at most L edges. Okay. Now, just consider a graph with n vertices. So if I am interested in finding the shortest path from one vertex to another vertex, then approximately how many intermediate edges can be considered? So n minus 1 edges can be considered, because n minus 1 edges are required for the spanning tree construction. And in the worst case, all those edges are required for the finding the shortest path from one vertex to the any other vertex. So in that case, the intermediate edges will be total n minus 1. Okay, so the maximum value of L is n minus 1 in case of n vertex graph. And here you can note here that this is initialized dist of u, and while subscript superscript is equal to 1, it means that dist of u is indicates that the shortest path from vertex v to vertex u, and indicating that at most single edge is considered. If single edge is considered, then it is nothing but your cost adjacency matrix of size n cross n. Okay, in cost adjacency matrix, we consider the direct edge present between each pair of vertices. If direct edge is present, then we will choose that cost. Otherwise, the cost is considered as infinity. Okay. So finally, it is saying that dist of u, where superscript n minus 1 is the length of the unrestricted shortest path from v to u. So this indicates that one for loop should be there, which is starting from 2 and it is ending from n minus 1. Okay, because dist of u and superscript 1, this is initialized by this cost matrix. So basically, what you can consider here, see, this is the characteristic equation for the dynamic programming. So if this dist of u and superscript k is equal to dist of u superscript k minus 1. So this is by considering at most k minus 1 edges, and here if we can considering k minus 1 edges, and but what is the provision here? Here provision is there for considering the at most k edges. So we can include one more edge here. So if cost of iu and dist of this expression is somewhat lesser than this particular expression, then we will select this. Otherwise, the previous considered thing was better as compared to this new expression. So that is the overall idea behind this. Now see the optimal substructure for this. What do you mean by optimal substructure? If we are saying that 1, 2, 3, this from vertex 1 to vertex 3, this is the shortest path. This vertex 1 to 2 and 2 to 3. This is the shortest path, and it means that 2 is some intermediate vertex on this path. It means that 1 to 2 should be optimal and 2 to 3 should be optimal. Means there is no such path present in the graph that is running from vertex 1 to vertex 2 and the distance of that particular path is less than 7. There is no such path in the graph G should present in this graph such that it is starting from vertex 2 and ending at vertex 3, and the cost of this particular path is less than minus 5. Okay, so this is the optimal substructure. Okay, first of all, we see the example and then we will look at the algorithm. Here we can see the shortest path, single source shortest path algorithm, and the source vertex selected is 1. So here we can note how we can compute this computational matrix here. So basically, when k is equal to 1, what is k? K is nothing but this superscript. It indicates the at most edges considered in this particular path. Okay, so dist of 1 is equal to 0. It means that 1 to 1. Okay, dist of 2 is nothing but 1 to 2. So 1 to 2, there is a direct edge present. Okay, dist of 3, it means that 1 to 3, there is a direct edge present. The cost is 5. Here you can note here that 1 to 3, if we, if sorry, for a 1 to 2, if we consider this path 1 to 3 and then 3 to 2, what is the path? What is the cost of this? 5 plus minus 2, that is nothing but 3. So 3 is far better than this 6, but we cannot consider this because the restrict. What is the restriction in this first row? The restriction in the first row is that the value of k should be 1. It means that for any path, only single edge can be considered. So here you can note that from 1 to 2, 3, and 4, there is a direct edge present, and the cost are this 6, 5, and 5 respectively. But there is no direct edge present from 1 to 5, 6, or 7. So that's why 1 to 5 initially it is considered as infinity. 1 to 6 is also considered as infinity. 1 to 7 is also considered as infinity. Now we will increment the value of k. So here k is starting from 2. Now when we consider this second row, it means that on each and every path, how many at most edges considered? 2 edges can be considered. Here in the third row, at most 3 edges can be considered. Here in row 4, at most 4 edges, and then at most 5 edges, and at most 6 edges. As you can note here, this is 7 vertex graph. So total, how many edges are required for computation of spanning tree? 6 edges are required. So that's why it is lasting with 6. Okay, now here you can note that this is the first part of the algorithm. It is taking four parameter as input. V is nothing but the source vertex. Cost is the cost adjacency matrix. Dist is that array. Dist of and what is the size of this dist vector? The size is nothing but the number of vertices in which dist of I is equal to cost of Vi, or we can say the shortest path from vertex V to vertex I. N is the number of vertices. Here we can note that it is nothing but the initialization for I is equal to 1 to n. Rest of I is initialized to cost of I. Here you can note just we are just considering whether there is a direct edge present from vertex V to vertex I. If it is present, then we are including this in this list. Otherwise, this cost will be infinity and this infinity will be assigned to this. Okay, it is nothing but this first row computation. Okay. After that, this loop is running from 2 to 6. What is the value of n here? The value of n is 7. So it is running from 2 to 6. That's why here you can see one loop which is running from 2 to n minus 1. It is nothing but k. K is nothing but that superscript which indicate that at most how many edges can be considered on that particular path. After that, you will see if 2 to 1. Okay, so 2 to 1 actually. So if we see this, it is nothing but 1 to 1. The cost will be 0 only. So here you can see source vertex is vertex 1. So this column is not getting changed. It will remain same. But what is this entry? This 3. This 3 indicate the shortest path from vertex 2 to, sorry, shortest path from vertex 1 to vertex 2. Now here you can note that if you want to go from vertex 1 to vertex 2, and how many at most edges can be considered on this path, at most these two edges can be considered. Okay, if two edges can be considered, then we can go via 1 to 3, we can go like this 1 to 3 and then 3 to 2. Now here you can see 1 to 2 and 2 to 3. What is the cost? Cost is 3. 3 is better than this 6. Okay, so this 6 is get overwritten by 3. Now just see this. What is this? This entry indicate the shortest path from vertex 1 to vertex 3. If you can note here, the direct edge from vertex 1 to vertex 3 is 5. But if you can consider two edges, then you can go via 4 also, like 1 to 4 and then 4 to 3. So this path is 3 and 3 is better than 5. So here 5 is get overwritten by 3. Okay, then 1 to 4. Here you can note that 1 to 4 is initially it is 5, and if you consider at most two edges, then also it will remain 5 because there is no direct, because there is no such path present such that it is considered by two edges and the cost of this particular path is less than 5. So it will remain 5 only. Okay. After that, it is getting changed. This cost of 5 and cost of dist of 5 and dist of 6, it is getting changed. Earlier it was infinity because single edge was the restriction. If two edges are considered, okay, then if I consider this 5, so there are two options. So I can go like this 1 to 2 and then 2 to 1. Sorry, 1 to 2 and 2 to 5. Or second option 1 to 3 and 3 to 5. So if I go via 2, what is the option? The option is this 5. And if I go like this, so the option is 6. So one option is 5, another option is 6. Which one is better? 5 is better. So you can note here, list of 5 is get updated and it is now 5. Similarly, if I update this list of 6, so if I consider two edges, then I can go via 4. So 1 to 4 and 4 to 6. The cost is 4, and infinity is get overwritten by 4. Finally, list of 7 by considering at most two edges. So I cannot reach from vertex 1 to vertex 7 by just considering two edges. So that is not possible. So infinity will remain infinity. So we consider this computation of the second row. Now here you can note that if this is my vertex, if I am interested in updating the vertex 5 for a list of vertex 5, so I must have see what are the incoming edges for this. What are the incoming edges for this? This is incoming edge from 2 to 5, and another incoming edge is this, which is coming from vertex 3 to vertex 5. Okay, so I will check list of 2 and list of 3 in the previous row. So list of 2 is this 6. I will not see this row if I am computing this row. I will see list from the previous row. That's why, because here k is equal to 1, and if I edge one more, if I add one more edge in this, then it will become two edges. And on the other side, if I consider this edge here at most two ages can also be considered. So if two ages are already considered, then if I add one more age like 2 to 5, then it will become three ages. That is not possible here, because in second row, what is the restriction? The restriction is there that only two ages can be considered. Now just look at the algorithm. What we are doing in that algorithm, this for loop is clear, which is running from 2 to n minus 1. Now, for each u such that u is not equal to v, means that u should not be a source vertex. So, which vertex we are talking about? This 2, 3, 4, 5, 6, 7. This vertex we are talking about. Okay, this should not be equal to the source vertex. The first condition. And second condition, u has at least one incoming edge. So, that u should have at least one incoming edge. So, we will perform for that u. Okay, so for each IU, what is IU? I is some vertex such that there is an edge from vertex I to vertex u. Okay, so we will compute this. If dist of u is greater than dist of I plus cost of IU, then we will update this dist of u plus dist of u plus cost of IU. Just see this example once again. See here. If consider this vertex 2. Okay, so vertex 2 will become my vertex u. So how many incoming edges are there? So two incoming edges are there. First one is coming from 1 and second one is coming from 3. Okay, if I consider this 1, so what is the dist of this 1? And the cost of this edge is 6. So 0 plus 6, this is 0, and 0 plus 6 is 6 only. Okay, now what is the dist of 3? Dist of 3 here I can note that it is 5u. So dist of 3 is 5u, and the cost of IU, I is nothing but this 3. So dist of this is greater than dist of I plus cost of IU. So this is smaller. This second expression is smaller. While computing this dist of 3, so I can just replace this. So I will update this, and this 5 is get overwritten by 3. Similarly, 6 is get overwritten by 3. Similarly, this 5 and 6 are get overwritten by 5 and 4. Okay. So like this, we are doing the computation. So total, how many loops are there, and what is the time complexity of this algorithm? Here we can note that this is first construct, which is running from 1 to n. This is running from 1 to n. So the time complexity of this construct is order of n. The k loop is running from 2 to n minus 1 times. 2 to n minus 1 means n minus 2 times. Okay, so approximately you can say that it is running k times. And for each u, such that u is not equal to v, and if it depends on the graph representation in the memory. If the graph is represented with the help of adjacency matrix, then we need to check for each and every vertex. And if the graph is represented with the help of adjacency list, then we will compare we will consider the list or the edges directly. So for each IU in the graph, if this is if this condition is true, then we will replace this. Okay. So what is the fundamental operation in this entire algorithm? The fundamental operation in the entire algorithm is this comparison that we are doing in this. Okay. Now total how many comparisons are there? This is outermost for loop, this is inner for loop, this is inner for loop, and this is the innermost for loop. Here you can note that it is also running n times, approximately. And so the time complexity of the entire construct is order of n cube when graph is represented with the help of adjacency matrix. And if the graph is represented with the help of adjacency list, then the time complexity from this for loop to the end, the time complexity will be order of e only. And the outer for loop is running n times, so the final time complexity of this algorithm will be order of n multiplied by e. So order of ne is the final time complexity. Now we will see several algorithm based on these problems or this category of algorithm formation known as dynamic programming. The fluid Marshall algorithm for all pair shortest path computation is based on it is based on dynamic programming approach. Okay, so this is the match. The Prim's algorithm for minimum cost spanning tree. Prim's algorithm is based on greedy approach. Okay, so P is matched with 2. So how many options are there like this? P is matched with 2. So option C and option D are there. Okay, what is the next? Next is Q is matched with 3 and Q is matched with 1. So just check. Fluid Warshall algorithm is based on dynamic programming approach. So Q is based on 3. So option C is correct. There is no to which R is mapped and to which S is mapped. But just have a look. What is this? This merge sort is based on DAC approach. So R is based on fourth option. So R is mapped with 4, and the Hamiltonian circuit is nothing but the backtracking problem. So S is mapped with this one. Okay, so option C is the correct option here. Okay, so this is another example. It is nothing but the monotonically increasing sequence problem. Monotonically increasing sequence problem is nothing but one in a sequence is given, and we are interested in finding the we have to select some of the number such that the selected number previous selected number is lesser as compared to the next selected number, and the length of this sequence or length of this chosen number should be maximum. It is known as monotonically increasing sequence. Okay, so for this we will form the dynamic programming formulation based on this. Li is equal see here the a is ranging from 0 to n minus 1. So Ln minus 1 is equal to 1 if we are considering only last element. Okay. And if Li is equal to 1 plus Li plus 1, when this Ai is less than Ai plus 1. Okay. So previous element should be less as compared to this element, then we will consider 1 plus this. Otherwise, it will remain 1. Okay. It is nothing but dynamic programming formulation. So the correct option here is the algorithm usage, the dynamic programming paradigm. Paradigm is nothing but the algorithm design approach. The tightest bound on the number of comparison in the worst case for comparison based sorting is of the order of n log n. Okay, which algorithm we have seen for sorting algorithm for comparison based sort? There are basically two categories are there: comparison based sort and the other category. What is the other category of sorting? That is based on the nature of the elements. Okay, in which we compute this radix sort, counting sort. Okay, so in comparison based algorithm, we have seen this algorithm selection sort, bubble sort, insertion sort. All these selection, bubble, insertion, the time complexity is n square. However, the other category that is based on DAC approach, like merge sort algorithm, quick sort algorithm, the time complexity of this is n log n. If you consider the quick sort algorithm, the time complexity of quick sort in worst case is n square. However, in another algorithm for merge sort algorithm, the average case, best case, and worst case time complexity is n log n only. Okay, so what is the tightest lower amount? The tightest lower amount is n log n. Okay, then which one of the following algorithm design paradigm is used for finding all pair shortest distance in the in a graph? So all pair shortest path can be find out with the help of dynamic programming approach. Okay, so one question is there. It is based on matrix chain multiplication. 4 matrices are given: A1, A2, A3, A4 with the dimension 10 cross 5, 5 cross 20, 20 cross 10, and 10 cross 5 respectively. And it is saying that the minimum number of scalar multiplication required to find the product. So we are interested in finding the optimal sequence of matrix multiplication. So in which sequence we are interested in multiplication? So what is the initialization part? Initialization part is A11, 22, 33, and 44 is initialized to 0 only. Okay. So after that, we will consider A12, then A23, and then A34. As we can note here, A12, A23, A34. Okay, here the difference between I and J is 1. Okay, how can we compute A12? This first matrix is multiplied with second matrix. So the total number of scalar multiplication will be 5 multiplied, 10 multiplied by 5 multiplied by 20. It is nothing but 1000. So here we can note 1, 2, 2, 3, and 3, 4. All are coming out 1000. After that, this difference is get increased, and the number of subproblem is getting reduced here. So here we can note that the difference is 1, and the total number of subproblems in this in the first phase is 3. After that, this difference is get increased. In this, we can compute A13 and A24. See, A13 and A24. Here the difference between I and J is 2. Okay, we can apply that characteristic equation and we will compute this. So here we will take minimum of this 2000 and 1500, and for which it is minimum, it is stored in some variable k. And we similarly we can compute A24 and we will store this, and it will take the minimum of this. After that, finally, we will compute A14. So this is phase one. Three sub problems are there. Difference between I and J is 1. Here, the second phase of the matrix chain multiplication, the difference between I and J is 2, and the sub problem is also 2. In the last phase, only single sub problem is there. The difference between I and J is 3. So finally, we will be computing A14. A14 is nothing but the minimum number of scalar multiplication required for the actual multiplication from A1 to A4. Okay, so for this we are having three options for K. So first will be 1, second will be 2, third will be 3. So for this we are having these three expressions. So which one is minimum? This 1500 is minimum. Okay, so we will take this 1500 is the example. 1500 is the is put here. Okay, here we are just interested in the scalar multiplication. If we are interested in the optimal sequence, then we can also find the optimal sequence for which value of k this expression is getting minimized. On that basis, we can identify this is the probable sequence. So A2, A3 is first multiplied. The result of A2, A3 is getting multiplied with A4, and finally A1 is multiplied with that entire result. Once again, say next problem is also based on this matrix chain multiplication. What does it say? Is assume that multiplying a matrix G1 of dimension P cross Q with another matrix G2 of dimension Q cross R. Here we can note that the number of columns in first matrix, that is G1, is equal to the number of rows in second matrix, that is G2. Requires total how many multiplications? PQR multiplications are required. Computing the product of n matrices G1, G2, G3 up to Gn can be done by parenthesizing in different ways. So define Gi and Gi plus 1 as an explicitly computed pair for the given parenthesization if they are directly multiplied. Okay. For example, if these six matrices are given, so this could be a sequence. First, G2, G3 is multiplied. This result is multiplied with G1. Then G5, G6 is multiplied. Then this result is multiplied with G4, and finally these two results is getting multiplied. So what do you mean by explicitly multiplied pair? So here we can note that G2, G3, these are the explicitly multiplied pair, and this G5, G6 are the explicit multiplied pair. So in this question, it is asking that consider the matrix multiplication in which five matrices are there, F1, F2, F3, up to F5. And these dimensions are also given, 2 cross 15, 15, 25 cross 3, 3 cross 16, 16 cross 1000. And the question is that in the parenthesization of this F1, F2, F3, that minimizes the total number of scalar multiplication. Means we are interested in applying the matrix chain multiplication problem, and it is saying that explicitly computed pairs. So here we can see this is one parenthesization example between G1 to G5, G6. Explicitly multiplied pairs are G2, G3, and G5, G6. Okay. So for this, it is asking that which are the explicit multiplied pair. So we can just guess here. See, this is first, second, third, fourth, and fifth. If we multiply third and fourth, if we multiply third and fourth, so how many multiplications are required? It is 3 cross 16. It is 16 cross 1. So if I multiply this, so how many multiplications are required? 3 cross 16 cross 1. Total, only 48 multiplications are required. So if we compare this 48 multiplications with any other thing like F1, F2 is, if F1, F2 is multiplied, then 2 cross 25 and 25 cross 3 is multiplied. So how many multiplications are required? 2 multiplied by 25 multiplied by 3. It means that 150 multiplications are required. So here we can note that 48 are much lesser as compared to the 150. So F3, F4 should definitely be there. Now see, how many options are there with F3, F4? So this say B option is not selected here. Okay, so F1, if we are considering F3, F4, then there is no need of checking F4, F5 because we are explicitly doing F3, F4, and that result is going to get multiplied with F4 or with F5 or any previous computations. So two options are remaining now: option A and option C. In option A, F3, F4 are there, and in option A, F1, F2, and F3, F4 are there. So I just need to decide whether F1, F2 is an explicitly computed pair or not. So for this, I can just calculate all these things in the phase manner, and after that I can find out the optimal sequence, and on the basis of that sequence I will answer this. Otherwise, if F1, F2 is not there in the option A, or some other options is there, then without calculation, I can simply tick on the option C. Okay. Then next algorithm given below are some algorithm and some algorithm design paradigm. So match the above algorithm on the left to the corresponding design paradigm they follows. So basically, two groups are there. In the first group, this Dijkstra shortest path is there, fluid version, then binary search, and then backtracking. So it is Dijkstra shortest path. It is simply solved with the help of greedy approach. So 1, 2, 3. Okay. So here we can note that 1, 2, 3, then 1, 2, 3, 1, 2, 3. Okay. Here we can note that this 1, 2, 1, sorry, 1, 2 first. This is only first option. By looking at the option itself, what we can decide this, we can just conclude that 1, 2 first is the wrong option, because in all these options B, C, and D, 1, 2 third is the option is present. Okay, so basically this option, correct option should lies from in between B to D only. So option A is straightforward rejected here. Okay. Then the second thing, okay, second is fluid Warshall algorithm. Fluid Warshall is based on dynamic programming. So 2 is mapped with this 2. So here we can note that 2 is mapped with this 2 and 2 is mapped with 2. So now we are having only two options remaining, option C and option D. Option B is not selected because in option B 2 is mapped with 3. So fluid Warshall algorithm cannot be solved with the help of graded design approach. Now three options are there. The, two options are remaining, C and D. So in third, what is saying? It is 3 is mapped with first, and here also 3 is mapped with first. There is no need to check 3 to whom it is mapping, because it will be definitely mapped with 1 only. Okay, just look at fourth. Fourth is backtracking. Backtracking is solved with the help of depth first search. So 4 is mapped with 4. So 4 is mapped with 4, and here the correct option is C. Okay, and if you want to look at this to which or how 3 is mapped with 1, so 3 is a binary search problem and it is a sorted sequence. It is based on DAC approach. So 3 is mapped with 1. Correct option is option C. Okay, now this is the next question. Consider two strings A and B. Okay, so A is QPQRR and B is PQPRQRP. Let X be the length of the longest common subsequence. We have seen this. What is longest common subsequence? Where between A and B, and Y is the number of such longest common subsequence. See, the length of the longest common subsequence is 4, and it might be possible that we are having more than one longest common subsequence present with the same length. Now, X, see the difference between X and Y. X is the length of the longest common subsequence, and Y is nothing but the number of such longest common subsequence. So it is asking X plus 10Y. Just check what is the length of longest common subsequence. First, we will compute the value of X, and later on, we will compute the value of Y, and we will evaluate this expression. So if I just see without computation or without formation of that table, I can just conclude whether the length of longest common subsequence is 5 or not. Because see, how many characters are there in first sequence? 5 characters are there. So QPQRR, is QPQRR present in option in second string? So Q is present, P is present, then Q is present, R is present, last R is not present. So it concludes that length of the longest common subsequence cannot be 5. Okay, now we will check length of the longest common subsequence is 4 or not. Okay, just see here QPQR. So here QPQR is present. Definitely the longest common subsequence, the length of this longest common subsequence will be 4. So what is the value of X? The value of X is 4. x with the length of the longest common subsequence. So it is 4. Now second question, what is the value of y? So how many total possible options are there? First match is this QPQR. Okay, so QPQR. This is also present in both the string. Length is 4. Now see another one. Just take it QQ double Q double R. So this is first Q, second Q, single R is there. So double Q double R is not possible. And then another thing is just check PQRR. So if PQRR is present, PQR and R. So PQRR is present. Again, the length is 4. So we found the second sequence. Okay. First one was QPQR. Second sequence PQRR. Just check one more. This QPRR. QPRR. So see, first one was this. First one was QPQR. Second one QPRR. And now we are checking third one, that is uh, PQRR. So all these three options are present in both these strings, and each length, the length of each of these is 4. Okay. So what is the total options for y? The value of y is 4 because y indicate y be the number of such longest common subsequence. So first y is this QPQR, second y will be QPRR, third y will be PQRR. Okay. So here the value is expression is this 4 plus 10 multiplied by 3, it is nothing but 40. Sorry, 4 plus 10 multiplied by 3. So it is nothing but 34. 34 is the correct option. Okay, 34 is the correct option here. Okay, now see the second one more question. Four matrices are there, M1 to M4, with the dimension P cross Q, Q cross R cross S, and S cross T respectively, can be multiplied in several ways. This problem is also based on matrician multiplication. For example, when we multiplied this M1, M2, M3, M4, and the result is the total number of multiplication is this. When we multiplied this, and the total number of scalar multiplication is this. What is saying, if P is equal to 10, Q is equal to R is equal to, sorry, Q is equal to 100, R is equal to 20, and S is equal to 5, and T is equal to this. And the total number of scalar multiplication needed is, so what basically it wants, we want to apply the matrician multiplication algorithm for this problem. Okay. So explanation is this. If we apply matrician multiplication phase wise, like in first phase, how many sub-problems are there? M1, 2, M2, 3, M3, 4. We will compute this. After that, in second sub-problem, we will be computing M1, 3 and M2, 4. In the third phase, we will be computing M1, 4. On the basis of that final computation, the total number of scalar multiplication will be computed as 19,000. So these are the total number of scalar multiplications. Okay, another question is there. Subsequence of given length is just the given sequence with some element left out. So basically, it is a definition of subsequence. So we are given two sequences. First x and second is y. In x, m characters are there. In y, n characters are there, respectively. And the index are starting from 0. Okay. So in x, the index will be varying from 0 to m minus 1. In y, the index will be varying from 0 to n minus 1. We wish to find the longest common subsequence, the length of the longest common subsequence, LCS of xm and yn, as this lmn. So where an incomplete recursive definition for the function to compute the length of LCS of xm and yn is given below. So L of ij is equal to 0 if I is equal to 0 or j is equal to 0, or expression 1 if I and j is greater than 0 and it is a match, that we have already seen. Okay. And if I and j is greater than 0 and x of I plus I minus 1 is not equal to y of j minus 1, then some expression 2, it is nothing but that max of these two. Okay. The value of Lij could be obtained by dynamic programming based on the correct recursive definition of Lij of the form given below, using an array Lmn, where m is equal to m plus 1 and n is equal to n plus 1, such that Lij is equal to small Lij. So which one of the following statement would be true regarding the dynamic programming solution for the recursive definition of Lij? So what is the first option? The first option is that all elements of L should be initialized to 0 for the value of Lij to be computed, to be properly computed. See, it is not, it should not be true, because only first row and first column should be initialized to 0. Rest entry can be defined or can be computed properly without initializing it to 0. Then the second question, the value of second option, the value of Lij may be computed in row major order or column major order. So this is probably correct option, because you can compute this row wise or column wise. Means first row is computed, then second row is computed, then in first row first element is computed, after that second entry is computed, then third entry, and so on. So it can be computed row wise or column wise. Those option B should be the correct option. Just look at the another options. So option C, the value of Lij cannot be computed in either row major order or column major order. So option C is just a contradiction to option B. Option C is not a correct option. B is the correct option. Then C, option D, L of PQ needs to be computed before L of RS if either P is less than Q or Q is less than S. So see, we are talking about the computation of PQ, so P and Q, before this R and S. So why it is not true? Because there is a logical or between this. Okay, because see, P should be less than R and Q should be less than S. Okay, then only it is possible that this LPQ should be computed before LS. It should not be like that. Here P is less than R and Q is greater than S. So it is not possible. So in that case, this option D is also not the correct option. So here option B is the correct option. Okay, thank you.